Imagine this. You finally find the perfect research paper for your project. It has everything you need: cutting edge ideas, real experiments, powerful insights. You open it excited, but within minutes, that excitement turns into confusion. The sentences are dense, the terminology feels overwhelming, and every paragraph raises more questions than answers. You try to push through reading lines again and again, but it just doesn't click. And at some point, you think, there has to be an easier way to understand this. Now imagine a different experience. You take the same research paper, upload it into a simple web app, and ask one question: explain this paper like I am a beginner. Within seconds, you get a clear, structured explanation, main idea broken down, key concepts simplified, and even examples that actually make sense. It feels like someone sat down, read the entire research paper for you, and explained it to you like a teacher who truly understands how to teach. That's exactly what this project does. But here's the interesting part: this isn't just some chatbot giving random answers. Behind the scenes, there's a complete intelligence system working step by step. It reads the document, breaks it into smaller pieces, understands the meaning, searches for the most relevant information, and then carefully generates an answer based only on that content. It doesn't just guess, it explains, and that's what makes it powerful. In this video, we are not just building a cool app, we are building a system that shows how modern AI actually works in real world. You will first see a live demo where we will upload a real research paper and get instant explanations. Then we'll break everything down step by step. No heavy theory, no confusing part, just clear, practical understanding of how each part works and why it matters. By the end, you won't just know how to build this research paper explainer. You will understand the exact ideas behind the tools that are shaping the future of AI. So, if you have ever struggled with research papers or wondered how AI can actually read and explain documents, this is going to be worthy of your time. So, let's get started. So, you just saw the demo. We uploaded a research paper, asked a few questions, and instantly got clear explanations. But here's the real question: what exactly happened behind the scenes? Because this isn't just a simple chatbot. There's a complete system working step by step to make this possible. So, before we jump into the details, let's zoom out for a second. First, I will show you the full flowchart. This is the big picture of the entire pipeline, from uploading the PDF all the way to generating the final answer. Now, don't worry if it looks complex at first. You are not supposed to understand everything here. This is just to give you a mental map of how things are connected. Now, let's simplify it. At its core, the entire system can be reduced to just this: PDF, chunk, embed, index, search, prompt, AI, answer. This is the backbone of the whole project. We take a paper, break it down, understand its meaning, store it smartly, and search the right parts, guide the AI, and finally generate the answer. And now that you have both the big picture and the simplified version, let's start breaking it down step by step. We will look at each stage, understand the problem it solves, and see how everything connects together. So, how is this AI actually understanding a full research paper? Let's break it down step by step. The first problem is that the research paper is huge. AI can't process everything at once. So, what does the system do? It breaks the paper into smaller, meaningful parts. Now, instead of one big document, we have multiple smaller pieces that are easier to handle. But here's the next problem. Even after breaking it down, the system still doesn't understand text. It just sees words. So we convert each chunk into meaning using embeddings from sentence transformers. Now the system doesn't just read text, it understands what it means. Next problem is that now we have hundreds of chunks. How do we search through them quickly? So we build a fast search system using Facebook AI similarity search. This helps find similar meanings instantly. But wait, what if the user asks for exact words, like a specific term or definition? So we add another system using BM25. This one focuses on exact keyword matching. Now comes another challenge. Which one of these should we trust? Meaning or exact words? So instead of choosing one, we choose both. We search using both systems and combine the result. This way, we don't miss anything important. Now, we have the most relevant parts of the paper, but the AI still needs to answer properly. So we give it clear instructions: what to do, how to answer, and how detailed it should be. Now comes the most important step. The AI doesn't just guess, it actually reads those selected parts before answering. This is what makes this answer accurate and grounded. But what if the AI fails and doesn't respond? We don't stop there. The system automatically switches to another model, so the user always gets a response. And finally, the system generates a clean, structured answer based completely on the research paper. So basically, you upload a paper, ask a question, and the AI reads, understands, searches, and explains it like a teacher. So let's start with embeddings. Imagine this: you upload a 20-page research paper full of complex terms like neural architectures and optimization techniques. Now a user asks, how does this paper improve AI models? The problem: the exact words improve AI models may not even exist in the paper. This is where embeddings step in. Using a model from sentence transformers, your system converts every chunk of text into vectors, a list of numbers that capture meaning, not just words. Think of it like translating human language into a machine language of meaning. For example, increase model accuracy and improve model performance will have similar embeddings. So when the question comes in, it is also converted into a vector. Now, the system compares meaning instead of keywords. This is powerful because research papers often use different wording for the same idea. Without embeddings, your system would miss important information. With embeddings, it understands intent. It is like having a smart reader who says, I know what do you mean, even if the words are different. This is the foundation that makes your research paper explainer intelligent rather than just a keyword search tool. Now, let's look at vector search. Now imagine that your system has converted hundreds of chunks into embeddings. The next challenge is speed. When a user asks a question, you can't scan every chunk manually. That would be too slow. So you bring in Facebook AI Similarity Search. Think of Facebook AI Similarity Search as a superfast search engine for vectors. Let's say your research paper has a section explaining gradient descent. A user asks, how does the model learn? Even if the words don't match exactly, Facebook AI Similarity Search quickly finds the chunks with similar meaning by comparing vector distances. The closer two vectors are, the more related they are. It is like Google Maps for meaning. It finds the nearest idea instead of the nearest location. This allows your system to respond almost instantly. Even with large documents, in your research paper explainer, Facebook AI Similarity Search ensures that the most relevant explanations are retrieved within milliseconds. Without it, your system would feel slow and inefficient. With it, users get fast, accurate responses, making the experience smooth and professional. Now, let's focus on BM25. Let's say a user asks, what is CNN mentioned in the paper? This time, the exact words matter. If the paper literally contains CNN, you want to find those exact sections. This is where BM25 comes in. Unlike embeddings, BM25 focuses on keyword matching. It checks how often a word appears in chunk and how rare the word is across the document. So if CNN appears multiple times in a section, BM25 will rank it higher. Think of BM25 as a strict librarian. It doesn't intercept meaning, it just says, you asked for CNN, here are all the places it appears. This is especially useful in research papers where specific terms, formulas, or abbreviations are important. Embeddings might understand meaning, but they might miss exact matches. BM25 ensures nothing important is skipped. In your system, this acts as a backup mechanism, ensuring precision when users ask direct or technical questions. Now, let's look at hybrid retrieval. Here's where your system becomes truly powerful. Instead of choosing between embeddings and BM25, you combine both. Imagine a student asking, explain how training improves results. The paper might say, optimization increases accuracy instead. So, embeddings will catch this. But if the student asks, what is equation 3, BM25 will catch exact matches. Your system runs both searches and merges the results. This is called hybrid retrieval. Think of it like having two assistants. One understands meaning deeply, and the other is excellent at spotting exact terms. Together, they give you the best answer. This approach is used in real world AI systems because it improves accuracy significantly. In your research paper explainer, hybrid retrieval ensures that the users get both contextually relevant and precise answers. It reduces the chances of missing important information and makes your system feel smarter and more reliable. Now, let's look at RAG, also known as Retrieval Augmented Generation. Here comes the main highlight of your project. Imagine asking ChatGPT a question about specific research paper. Normally, it might guess or give a general answer, but your system does something smarter. It first retrieves relevant chunks and then sends those to the model like Llama. This approach is called Retrieval Augmented Generation or RAG. It is like giving the AI an open book during an exam. Instead of relying on memory, it reads the actual paper before answering. For example, if the paper explains a new algorithm, your system fetches the section and asks the model to explain it. This reduces hallucinations and ensures accuracy. In your research paper explainer, this is what makes the system trustworthy. Users are not getting random answers, they are getting explanations grounded in the document. This is a huge step forward from traditional chatbots. Now, let's look at text chunking. Research papers are long and complex. You can't send the entire paper to the model at once, so your system breaks it into smaller chunks. Imagine reading a book. You don't remember the entire book at once, so you remember it chapter by chapter. Your chunking function splits the text into manageable pieces while keeping sentences intact. For example, a section explaining an algorithm becomes one chunk, while another section explaining the results becomes another. This helps in two ways. First, it makes embeddings more accurate, and second, it improves retrieval. If chunks are too large, the system might retrieve irrelevant information. If they are too small, context is lost. Your chunking balances both. In your research paper explainer, this ensures that when a user asks a question, the system retrieves the most relevant and complete explanations instead of random fragments. Now, let's focus on dense versus sparse retrieval. Your system uses both dense embeddings and sparse BM25 retrieval. Let's understand this with an example. Suppose a user asks, how does the model reduces error? The paper might say, minimizing loss function. Dense retrieval understands that reduce error and minimize loss mean the same thing. But if the user asks, where is the loss function defined? Sparse retrieval or BM25 will find the exact matches. Dense is like understanding meaning, while sparse is like matching words. Both of them are important. By combining them, your system handles both types of queries effectively. This makes your research paper explainer versatile. It works for both conceptual questions and technical queries. This dual approach is the key reason why your system performs so well. Now, let's look at prompt engineering. Imagine you retrieve the perfect chunks, but how do you make the AI respond properly? This is where prompt engineering comes in. Your system doesn't just ask a question, it gives you detailed instructions. It tells the model to use only the provided context, avoid guessing, and return structured JSON. It even adjusts explanations based on user level. For example, a beginner gets simple explanations, while a researcher gets detailed analysis. This is like giving clear instructions to a student before an exam. Without this, the model might give vague or incorrect answers. In your research paper explainer, prompt engineering ensures consistency, accuracy, and usability. It turns a general AI model into a specialized research assistant. Now, let's look at model routing. In real-world applications, models can fail, APIs can time out, or return empty responses. Your system handles this using model routing. It tries multiple models one by one until it gets a valid response. Imagine calling different experts. If one doesn't pick up, you call another. This ensures that your system always responds. In your research paper explainer, this makes the system reliable and production ready. Users won't experience failures because your system has backups. This is a practical engineering feature that many beginner projects miss. Now, let's focus on context aware question answering. Finally, everything comes together. A user uploads a research paper and asks, explain the main idea simply. Your system retrieves the relevant chunks, builds a structured prompt, and generates an answer grounded in the document. It even cites page numbers and formats the response. This is context aware question answering. Instead of generic answers, users get precise explanations based on their document. In your research paper explainer, this creates a powerful experience. Users can understand complex papers easily without reading everything. It is like having a personal tutor who reads the paper for you and explain it in your preferred style. Now that we have understood how the entire system works conceptually, let's bring it to life through the power of coding. We'll go step by step and see how each part of the pipeline is actually implemented, connecting everything from PDF processing to generating the final answer.